Hi guys, hope you all are doing good. So today in our video we'll be looking into the recursion. So recursion is considered as one of the most important concept to crack the interviews as well as the toughest concept. So a lot of small size companies as well as a large scale companies will be asking the questions on recursion, not directly but indirectly, as a lot of topics like permutation, subsequence, trees. So these sort of things are based upon the recursion as well as DP also. So one will be giving up when the recursion topic arrives while he is preparing to crack the interviews of a big tech giants. So that is the reason recursion takes a lot of practice. So one will be getting confident in recursion as well as perfect in recursion only if he practices a number of problems as well as the approaches. So what is recursion basically? We'll be starting from that. So what is recursion? So for example, a small definition of recursion is: recursion is a technique of function call inside another function or in itself. So this is how the recursion works. So basic syntax of recursion I would like to give you is: so as I said you, recursion is a function call in itself. So this is the basic syntax of recursion as well as with a base case. Why base case is important? Since we are calling function inside the function, so it will be run into the infinite loop. To avoid infinite loop, as well as, or we can consider to stop the flow of recursion. So whatever the problems on recursion you will be seeing, so the base case plays a vital role. If there is no base case, the function run into the infinite loop and you will be getting an error called stack, out of stack you can consider as, sorry, like memory out of stack. Hence, when you look into this error case, you can think of one thing: why here we got a keyword as a stack? Because recursion works completely in a stack memory. Since it is a function, it will obtain a stack space obviously. So what is stack? What is stack? I guess many of you might know. So stack is a memory. So whatever the function calls you will be doing, so it will be obtaining certain memory. So that is nothing but a stack. So what is the flow of stack? So stack flow is last in first out. It works on the principle of LIFO. So till now it is clear that recursion is a technique of function call inside its own function. And also we have seen the syntax of recursion as well. So function inside itself, function calling inside itself, as well as there is a base case. And we have learned about the memory obtained during the recursion. So it completely works on the stack memory. And also one of the important key point I would like to know, I would like to tell you that stack keeps the copy of every method like it creates a new copy every method called during recursion. So we have learned what is recursion, as well as syntax of recursion, as well as the memory obtained during the recursion. So these three basic principles we have learned, but we failed to learn why recursion. So basically, recursion is a technique which solves complex problems in a simpler way. And also, every call of recursion, I mean recursive function, makes the problem shorter. So these are the two basic concepts why we need to use the recursion. So we'll be looking with the examples as well, and also types of recursion. So there are many types of recursion, but we will be learning about two important concepts today, which is linear recursion. I guess these are enough to know the flow of recursion. So linear recursion as well as binary recursion. So what is linear recursion? What is linear recursion? So linear recursion, in the sense, it works in a single direction. As the name suggests, linear. As the name suggests, linear, it works in a single direction. So most of the linear recursion problems could be easily able to solve by the iterative approach. One of the example, good example for this, for solving of this linear recursion is factorial. Solving factorial of a number. So let us consider we are solving a factorial of 6. Or let me take shorter number, the 4 maybe. So how the iterative approach works? So we'll be running a loop. So we'll be seeing the iterative example. So we'll be seeing the example 1, which is iterative. Let me erase this. So let us move from iterative to the recursion approach. So maybe I need a variable to store the result. So let it be 1 initially. And I'll be running a loop. Let us consider we need to find a recursion of n equal to 4. Factorial of n equal to 4. So we'll be running a loop from n to 1. So we'll be running a loop, then we'll be multiplying to that result. So when n is 4, so let's just analyze this flow. So when n equal to 4, so the second step here we'll be getting, so 1 into 4, which is 4. So now the result is 4. So let us keep in this way. So we'll be storing the values of n as well as results, n and result. So initially n is 1, so result will be 1 into 4, which is 4. Then n is 3, then the result will be 4 into 3, which is 12. Next n is 2, then result will be 12 into 2, which is 24. Next n is 1, the result will be 24 into 1, which is 24. So output is 24. So next we will be seeing the recursive approach of this flow. So as I said to you, so the same number factorial will be finding out n equal to 4. So factorial of 4 will be finding out. So as I said to you, recursion is a function call itself. So factorial of, as we have seen in the syntax, as you can see here, so function call inside itself. So factorial of n, maybe n we can consider, we make it more clear. So function call itself. Let me just write it into the center. So factorial of n. So function call itself. Okay. And also there is a base case to stop this function. So when we consider the iterative approach, when we are stopping this call, iterative call, so whenever it reaches to the 1, whenever we are looping it from n to 1, as you can see here, we are looping it from n to 1. So whenever it reaches 1, whenever your n reaches 1, we are stopping the loop and returning the answer. So obviously base case will be 1. If n equal to 1, just return. I'll be returning 1. So return 1. So n into factorial of n minus 1. I'll be explaining you why this line, from where this line came. I'll be explaining you. So let us analyze few things. Sorry. Let us analyze few things. I'll make this a little smaller and move it to a side. Okay. So we have a stack memory. As I said you, recursion obtains stack space. Obviously the function calling obtains the stack space. So in the first step, so we'll be analyzing it step by step. In the first step, n is 4. And does it reach the base case? No. No, it does not. So we'll be returning n into, so n is 4 into 4 minus 1. Again this function call will go. 4 into 4 minus 1 won't be getting called, as this is only the function. So it will go to the top. N minus 1 is 3. Factorial of 3, again it will be getting called. So it will be calling factorial of 3. Does it reach the base case? No. N is 3, not 1. So 3 into 3 minus 1. Again it reaches to the top. Again it calls itself. So now n is 2. Does it reach the base case? No. So in line number 3, 2 into 2 minus 1. So here again it will make a call to itself. So now n is 1. Does it reach the base case? Yes, it does. So it will return 1. So as I said you, stack is last in first out. So it will return 1 to this method. So it resolves method by method as we have stored the copy of methods inside the stack. So it resolves method by method. And also it makes problem shorter. So whatever I have explained you will be analyze it over here. So in this method, so what we have received the answer 2 minus 1 answer what we have received from the top as 1. So 2 into 1 is 2. 2 into 1 is 2. So 2 will be returned to this method. 2 will be returned to this method and this will be removed from the stack. This will be removed from the stack. So what solution we have got from the 3 minus 1? If we run 3 minus 1 function we consider it as method 2. So 3 into 2 is 6. It returns 6 down. So this will be removed from the stack. This will be removed from the stack. And it reaches to the here. So what we have received from 4 minus 1 method as 6. So 4 into 6 is 24. Now 24 reaches to the main and logs the output. So output is 24 and this stack space is empty. So understood? So this is how the linear recursive flow works. This is how the linear recursive flow works. So if you want to analyze time and space complexity as well, so time complexity is big O of n as the recursive call is being made n times. So if n is equal to 4, so 4 times this recursive call has being made. And also space complexity depends upon the input. So it obtained the 4 copies of the method in the stack. So we can consider as n. So it is also depending upon the stack space. So sorry, this depends upon the stack space complexity. Stack space obtained is n. So this is the linear recursive example. So next we'll be considering it next we'll be looking into the binary recursive example. So I guess things are getting more clear. So sorry, binary recursive. So as the name suggests binary, so it will be bidirectional. So let us, I'll be explaining you with the example bidirectional in the sense. I'll use the blue pen only. So let us consider we'll be solving a problem of Fibonacci. So Fibo of n. So if we have n equal to 5, the general mathematical approach, what is the Fibonacci? So Fibonacci of 0 is 0. Fibonacci of 0 is 0. The Fibonacci of 1 is 1. and Fibonacci of 2 is the sum of previous two. So 1. And Fibonacci of 3 is sum of the previous two, which is 2. Fibonacci of 4 is sum of previous two, which is 3. Fibonacci of 5 is sum of previous two, which is 5. So I'll be analyzing this with a simple diagram, how the bidirectional concept works. So let us consider we have 5. We are trying to find the Fibonacci of 5. So we need the Fibonacci of 4 as well as Fibonacci of 3, as you can able to see in the flow here. So to resolve the Fibonacci of 5, we need this both, Fibonacci of 4 as well as Fibonacci of 3, not 2 and 3. These are the results of this Fibonacci. And also for resolving the Fibonacci of 4, we need two more things, the Fibonacci of 3 as well as Fibonacci of 2. To resolve the Fibonacci of 3 over here, we need two things. As you can see, Fibonacci of 2 and Fibonacci of 1. Once again, here Fibonacci of 2, Fibonacci of 1. To resolve 2, we need Fibonacci of 1 and 0. To resolve 2, we need Fibonacci of 1 and 0. And also here to resolve 2, Fibonacci of 1 and 0. So this is being solved bidirectionally, as you can see in the diagram. So 5 is dependent upon 4 and 3. Then 4 is dependent upon 3 and 2. So here 3 is dependent upon 2 and 1. So this is how binary recursion works. So let us analyze it with a problem by resolving the problem. So I'll write, so example problem, Fibo of n. So Fibo of n can be written as the recursive way. In a recursive way, it can be written as Fibo of n minus 1. So here we have two directions, one is left and one is right. So if left and right gets solved, my answer will be obtained. Sorry. If left and right is solved, my answer will be obtained. I don't care about the rest of things. So recurrence relation comes out to be Fibo of n minus 1 plus Fibo of n minus 2. As you can see over here, Fibo of n minus 1, Fibonacci of 5 minus 1 is 4, Fibonacci of 5 minus 2 is 3. So if I get the solution for these two, Fibonacci of 5 will be obtained. As well as, what will be the base case? What will be the base case? This is the important point. What will be the base case? So base case will be, see here, as you analyze this flow, base case are 0 and 1. Base case are 0 and 1. For 0 it will be 0. For 1 it will be 1. Here also, if you could able to see this diagram, whenever we get 1 and 0, we will be stopping it, because it will result in the negatives. So negatives we don't want, as you can see the flow. So we can write the base case as So if n less than or equal to 1, so we will be returning n itself. Here is this. Return is important. Writing return is important. So whenever the stack sees return, it starts eliminating your stack space, like reducing your stack space by resolving the problem. So return is important. So recurrence relation will be return of, let us write in this way. So int left will be fibo of n minus 1, int right will be fibo of n minus 2. Sorry. And the answer will be L plus R. So return answer. So this is how making the complex problem into simple problems. So I don't care what rest of the problem does for me. I only care about my previous two cases. What is the Fibonacci of 4 and what is the Fibonacci of 3? So this is how it works. So let us analyze it. Let us consider we have a stack space. So I'll take this. Okay, so we'll be doing it with a simple. So let us consider the Fibonacci of 4. So 4 is, so as we know, Fibonacci of 4 is, we have seen here, Fibonacci of 4 is 3. So we need to get result as 3. So let us analyze it with a diagram. Let us take this below, or else make it small here itself. So I'll quickly write here, create a diagram for, so n minus 1 will be 3, and for this n minus 2 will be 2. So I don't need to care rest of the things, these two will be taking care of, 3 and 2. Again the Fibonacci of 3 will be 2 and 1, n minus 1 and n minus 2 respectively, and Fibonacci of 2 will be 1 and 0. So these both are base cases we need to stop, and Fibonacci of 2 is 1 and 0. So this is the diagram as well. So I'll make this smaller as well. Let us analyze it. So we have 3 steps. This is step 1. So this is step 2. This is step 3. So I'll remove this. Step 1, step 2 and step 3. Oh my god, this messed up. I'll quickly draw it again. Okay. So here also 1 and 0. Yeah. So it reaches to the, let us take stack as well at the down. So the first step is n equal to 1. N is equal to 1? No, as we have 4. 4, it will go to its left side. So this is stack. And next we have line number 1. Does it solve? No. Line number 2, yeah, it will again make its recursive call as n minus 1, as we have n as 3 in here. It will go to its left with 3 minus 1. Again n is equal to 2. Does line number 1 works? No, it won't work. So again it will go to as n equal to 2. 2 will be going to its left side. So 2 minus 1. So 2 minus 1 is 1 over here. So it is a base case. 1 is a base case. What it will do? It will return 1. So from here it will return 1. So 1 is returned here and this stack space is empty now. Again what 2 will does is it will go to its right side. So 2 now go to its right. It's going to its right. Then in right it reaches 0. Then in right, if 2 goes to its right, so it reaches 0 here. This one, line number 3 will work now. So since it is going to its right, n minus 2 is 2 minus 2. So this will become 2 minus 2. Again it will go with 0 here at the top. So it reaches the base case again, which is n less than or equal to 1. So here is 0. So this will return 0. Now 2 left is completed as well as right is completed. So the stack will be empty. Two is eliminated from the stack. Now since 2 is eliminated from the stack, so answer will be L plus R, 1 plus 0, 1 plus 0. So here 2 answer will be going as 1 plus 0 as 1 to the above. Then 3 will be moving to its right. This 3 will be moving to its right. Since it moves to its right, so 3 has 3 minus 2. Here it will be 2. As we know, moving towards right is n minus 2. This one, line number 3. So this is right. It will move towards its right. So from here 1, 3 minus 2 again calls a recursive function. So 1, it does its recursive call. So base case is reached. Line number 1 will be executed again. So this will return 1 over here. So this will also return 1. Now for 3, both left and right are done. Left and right are done. So this will return 1 plus 1 as 2. Line number 3 will be executed. 4 will be executed. The answer line. So 1 plus 1 as 2. And the stack will be empty. Stack will be 3 will be getting eliminated from the stack. So here it returns 2. Then next 2 is returned from here. Then left side will be covered. Right side of the 4 will be covered. Then here if it goes right side, line number 3 will be executed. 4 minus 2 is 2. Again 2. Here 2 will be going to its left side, which is L. 2 will be going to its left side with 2 minus 1. Line number 2 will be executed. Then again 1 we will be getting as this function call happens. Once again 1 we will be getting, then it reaches the base case. Then here it returns 1. It returns 1 to the from the left side of the 2. It returns 1 from the left side of the 2. So again this 1 will be eliminated from the stack. Then it makes a call towards its right side, which is line number 3 again. So this returns 1. Then right side it will go. So which is 2 minus 2. Right side in the sense n minus 2. 2 minus 2. So here 0 it will be. So again it is the base case. So this will return 0. So this side it will return 0. So again the 2 left and right both are completed. It will be eliminated from the stack with the answer, as left plus right is 1 plus 0 is 1. It will go to the 4. Now it will reach us to the 4. So 4 also left and right both are completed. So it will be getting eliminated from the stack. So the final answer will be left answer is 2. Left answer is 2. And right answer is 1. So answer L plus R, which is 2 plus 1 equal to 3. Output is 3. Output is 3. So this is how the binary recursion works. So this is how binary recursion works.